So my first question is, can everyone hear me? Can everyone hear me? Let me know. Okay, is the sound level okay? I've got a drink so I don't dry up today. This is a Coca-Cola drink. It's from the Czech Republic. It's like the cola they made when they couldn't get Coca-Cola during the Soviet times. Okay, so I'll wait until anyone else comes in the room. What are your questions? Well, I think some people have taken a stab at the difference between Bremsstrahlung radiation and strange radiation, but they're definitely not the same thing. I can't answer whether anti-hydrogen is the same as dark hydrogen. Thanks for the invite, Tara, to APEC. I hope you can join us, Mr. Lindstrom. Yeah, Gordon's done a fair job of describing Bremsstrahlung, and he's certainly described the strange radiation as more complicated. Okay, so I'm again trying something different right now. There are a lot of people that are interested in Lena in Italy, so in a moment I'm going to switch to the English translation of these Russian slides, but hopefully it's going to do an instant Italian transcription at the same time. Okay. Okay, we've got 15 people in the room. I think it's probably enough to get going. Yes, Gordon, heat does appear to accelerate the production of strange radiation. Hi Numatek. Hi Cookie. Well, can a candle tell us anything about plasma? Well, it's kind of a plasma, so. Okay, so I'm going to go ahead with the presentation. I hope this works. Again, I've got a slightly different setup here today. I'm trying to improve things for you. We'll get there in the end. Okay. Okay, so am I clear? Okay, so we've got 16. All right, so this is a presentation that was given on Wednesday of this week, and it is a presentation produced by Vladimir Alexandrovich Chizhov. And he is a candidate of Technical Sciences, Laureate of the USSR Council of Ministers Prize, and a corresponding member of the Russian Academy of Natural Sciences, and that's RANS. And he did this work at the Moscow FIZPRIBOR plant between 2020 and 2021. And it's going to address 3 areas. I'm going to give my best hash of it. I've already published before this the Russian version of this presentation that he gave, plus the questions and answers that were given by him to the questions posed by a fair group of the Russian community. And it's on the operation of the nickel hydrogen container at room temperature. Secondly, a physical model, the hypothesis of the occurrence of strange radiation. And then 3, on the penetrating power of strange radiation and protection against it. Okay, so I'm going to go through this. Like I say, the translation may not be perfect. I used Google Translate and then I proofread it and then I added a little bit of my own knowledge. And also when it comes to the physical model, this has already been presented by Baranov and Zatelepin, and by Zatelepin, and I think I've already shared those videos of that. I've certainly discussed it before, and we can get on to that. But I hope I can do a reasonable job of just getting the key points across. But from my point of view, what was really important to me to get this presentation out was that there are various groups that are using devices that should be producing strange radiation. And in fact, even welding plants and high spinning motors, in theory, should be producing strange radiation. And anything that really cavitates. So, you know, if you've got a propeller, an impeller in water, there's a good chance that you're going to be getting some strange radiation off that. And, you know, we need to consider these things for workplace safety over and above the LENA research. And I have this reactor called the Supernova, and the maker is not with us, and he was only 40 years old. And he was what really brought home the potential risks really personally to me. I mean, I spoke to other and have known other researchers that are now dead. And in fact, Yuji Bazhatov, which I'll refer to right at the end of this presentation, he was the organizer of the cold nuclear transmutation and ball lightning events in Russia for the best part of 25 years. And it was believed that his demise came at the hands of this unusual, strange radiation that comes out of this type of experimentation. And so the Russian community kind of like took a big pause and looked to really try and understand what this radiation is, how you can detect for it, and how you can shield for it. And so this is interesting work that I'm going to show you here because it builds on some of the understanding that I've been sharing over the last couple of years, that much of which I realized has been observed by the likes of Laureate and Tereshchikov and Bogdanovich, mostly recently in 2019. And I will draw upon some of my experience when referring to this work. So this work is really someone who has a lot of experience in experimentation and came in to investigate in 2020 this particular aspect of the radiation. Yeah, I put the captions in Italian deliberately because you get the English. You can look at the English captions on the YouTube when this has gone up and it's done its captioning. But I put Italian up here because there's quite a lot of Italian researchers in LENA, and they would like to be able to understand the presentations real time or shortly afterwards. So I'm trying something new because I want to be able to, when I make presentations to the Russians or to the Italians or to the Japanese, I want to be able to have a real-time transcription on there as I'm making those presentations. So that's why I'm using that. Okay. Okay, so moving forward. So the theoretical, so sometimes I don't quite know what this translation should be, and I've asked Zatelepin to do some confirmation of what it should be saying, and when that comes back to me, I will update the presentation as and when better translations come through for various aspects of it. And after this presentation, probably tomorrow, I will share both the English and the Russian versions of the presentation. And also I will be doing some work on stabilizing some of the videos and producing some GIF animations. But anyway, theoretical work on CGS started in 2016 and was reported by me at the seminars of the MSU physics department in 2016 with Bichkov, VL, and PFUR with Samsonenko, NV, and that is Nikolai Samsonenko. I had the pleasure of picking me up at the airport in 2015 when I first went to visit Alexander Parkhomov. So that was in 2016. So in this work, it was shown that one cannot discount the possibility of CBN in nickel hydrogen system if this process goes on a crystalline defect. And so some of these things I'm not going to be able to do justice to. And like I say, go and look at the Russian version of the presentation. But it's really the safety aspects that I want to focus on. So he's talking about monocrystals and real crystals, and actual real crystals have different types of boundary defects. And he started experimental with the thermal process, which he gave a presentation on the 13th of November 2019. So this is our fellow here, and just to clarify, this work is done by someone who's a serious researcher, as the first slide goes over there. So the thermal process with nickel hydrogen systems, that's nickel and sodium boron hydride and lithium aluminium hydride, were carried out in the LOM laboratory in Podolsk. So there's our happy fellow, and in the background you can see the reactor. This is a close-up on the reactor, and I assume, although I might not be correct in assuming, but I would assume that on the left-hand side you see the hydrogen bottle, and I think most of the rest of that is thermal insulation, and it's a standoff there, and maybe there on the bottom right you can see a water reservoir, and that might be for some calorimetry, and the power control unit in the foreground there, and what looks like a periodic table and a couple of house plants in the background. This is a thermal well. I'm not entirely sure where this is placed, but you can see it's into the warm part of the reactor, and this is maybe suggesting how that would be placed. So it may be the actual reactor unit. It says nickel reactor unit and measuring microthermocouple. And so it looks like they've got some sort of, might appear to be a metal boat. One would expect to use copper for good thermal conductivity. And there seems to be some package in there. It's not entirely sure what that's made of. And at one point he was asked, can you describe your reactor? And from the real-time transcription, I understood that he was a little bit cagey to specify what's in that little package there. But we know how to make various types of reactor in this nickel hydrogen system. We've done it with the MFMP, and those that have followed this space have observed a lot. Now it could be that the two kind of like insulated ceramic pieces in the foreground of that are resistance heater wire, or they could just be a structure that's supporting the boat. But anyway, you can see the thermocouple there on the center moving out to the right. And essentially what they're saying is at the temperature of 1000 to 1150 degrees C under PID power regulation, they saw sharp oscillations and by the thermocouple. And let's go back to the thermocouple. You see it's in alumina possibly sheath, I would expect, and it's going into the core of the reactor. Now, I don't actually know whether that is nothing more than a simple mixture of powders. It's entirely possible it is, but whether the whole thing was in a more sealed case, I don't know. So moving forward, so you can see these oscillations, and the temperature oscillations were 30 to 70 Kelvin, and so it's oscillating around a kind of mean by that. And of course, this 1000 to 1150 degrees C is over the temperature which Parkhomov would say that you are getting some, cold neutrinos being synthesized. And it's certain, in our case, in GS 5.2, we didn't see signal until we first went over 1000 degrees. And if you remember bang way back when, it was around this kind of temperature range that our reactor blew up. But that could have just been a pressure release from the lithium aluminium hydride that we had in there. Okay, so what they did was they also saw, they put some CDs on here, and you can see that this is probably inspired by the previous work of Zhigalov and Alexander Parkhomov, based on his 225-day reactor and his woodpecker reactor, that technique that was developed there. And it's quite good because aluminium obviously seems to interact with strange radiation or whatever this is, microball lightning or coherent matter, it seems to react with it quite strongly. But it can go through, obviously, aluminium. And having this air sort of polycarbonate and then aluminium, this multi-layer, it kind of it suggests that a good type of detector. Anyway, we'll move forward. They appear to observe tracks, which this may be a bad translation, but he says strange, and then he refers to it as incomprehensible radiation on CDs. And so he has three tracks here, and I think there's the sort of standard one, this zigzag track that you see, this kind of spiraling track in the center. Then there's ones where they appear to be changing direction, and this is very interesting for something I hope to be able to show you tomorrow, where you see many tracks changing direction. But the more interesting things about this slide are in the left-hand image, you see the track is splitting into two. And then on the right-hand side, you see this spot or ring type mark. And so these ones that they identified. Now, there is an open question out there that if you get a dust particle, like a little bit of grit or sand, on a CD and then you rub it, then you can end up with these three-body interactions. So if you get two CDs, and you get two CDs and you had a little bit of grit and they move around. Now, you can ask yourself whether that certainly is possible to create a three-body interaction look. And you could possibly say that the image on the left, where it's splitting, maybe the bit of grit actually broke into two and then did these two kind of split track things. Anyway, from my point of view, if I hadn't have seen the exact structure of strange radiation with the angles and everything captured from Echo Fuel in 2017, when it was cold, months after it was produced, it would have been easier to think that this is just a three-body interaction, but in the case of that detection, that was detected by a CCD on the webcam that you're watching me on right now, and that was using Cosmic Ray Finder. So it's unlikely that the CCD on this Logitech 910C sensor had a piece of dust and then it rolled around between two plates. It's just impossible. And for the structure to be essentially the same and have the same scale as typical strange radiation, for me that was a watershed moment, because it isn't on a surface that can be exposed to dust. Anyway, it does seem to produce a wide range of tracks, so we move forward. So they had, here's the schematic, and so there's some things I haven't translated in there. You've got iron and aluminium, the CD all the way at the bottom. You have the reactor, which is the red ellipse on the top left there, and you have some nickel and some aluminium, and it's going through all of that material and ending up affecting the CD. So it's going through iron, it's going through aluminium, it's going through probably plastic, aluminium oxide, nickel, and whatever the reactor was made of, which we argued maybe some copper or whatever, but actually it might actually just be nickel plate that's in there, looking at that schematic right now. So schematic sectional view of the thermal insulation and penetrating power of the strange radiation. So it's gone through 2 millimeters of nickel, 5 millimeters of aluminium oxide, a lot of 120 millimeters of whatever that is, aluminium of 0.1 millimeter, something else at 110 millimeters, another 0.4 millimeters of aluminium, and iron 2 millimeters before it affected the CD. The three-body interaction people would say you just got a piece of dust on the CD and accidentally scratched it. So you know, that's the question that is raised by that approach. 250 millimeters overall, 25 centimeters of dense solid material that it's gone through to affect that CD. So it should be noted, and this is important actually, because there was a whole lot of debate about whether AC or DC was the right thing to use with nickel hydrogen reactors. And he says here that it should be noted that that at the same process temperature, but with a DC supply to the heater, the oscillation amplitude decreased by a factor of 20 or more. A factor of 20 or more to 1.5 Kelvin instead of 30 to 70 Kelvin. So basically 1.5 Kelvin is you know, I would argue that was within error bars, but 30 to 70 degrees Kelvin is quite a shift. So perhaps this answers the question whether we should be considering AC or DC in these type of systems. And they show here some scales with the strange radiation track. So you've got the kind of like rolling ring or spiral, depends which way you look at it, and straight one in the top right there, and the rolling ring and spiral or whatever it is in the bottom left. And then here's a different depth, so you're focusing at a different depth or using different lighting between these two shots. So these are both times 500. Okay. Then he's discussing here the track pattern in the near surface plexiglass layer of the CD disc is an open air-filled plexiglass melt. Now, I don't know how they specifically determined that it was a melt, because the three-body interaction argument would suggest that you have this grit and it's displacing the material. A melt is more... It's more problematic for me because it's an amorphous material anyway, and so when it's moved out of the way. But I think probably people of this caliber, and we can't assume this, but people of this caliber would be able to determine whether this was a melt or a physical displacement. Anyway, this is suggesting that there is a spiraling going on, and bear this in mind when I talk about the things that I want to talk about tomorrow. This spiraling going on. So based on the mass of the molten polycarbonate CD, the energy of this strange radiation is estimated to be gigantic. 50 tera-electron volts. Okay? 50 tera-electron volts. Now, you get tera-electron volt protons. They come from the cosmos. They come from celestial events. And they cause your particle showers as they come into our atmosphere. This is where you normally get your environmental muons from. But this is down working in a reactor. And so 50 tera-electron volts. Now, this isn't out of the realm, and it's certainly similar to, and I think it was actually more than this, I can't recall, but the calculations done by SV Adamenko at the Proton 21 labs, they were talking about many tera-electron volts for the particles that they had observed. I think it was him and Vladimir Vysotsky, and they used a multi-layer dielectric insulator, semiconductor or whatever with an oil film on it detector outside of their reactor. So it was going through their reactor materials and interacting with this metal dielectric semiconductor with a oil film on it, and so that was their multi-layer detector. Of course, it's a lot more expensive than buying a bunch of CDs. Anyway, this is a lot of energy. Okay, so how to explain such an incomprehensible effect of such radiation and such energy, which Reactor LI in 2000 called strange or incomprehensible radiation. Its penetrating ability in crystalline solids and leaving tracks in amorphous solids where there is no long-range order in arrangement of atoms, i.e. frozen liquid. So what he's saying is that it's able to go through crystalline solids, but in amorphous material, it seems to leave tracks. And this would actually sit well with the observation that we have had in the Lion reactor, and before that in the plastic that I surrounded the Echo fuel with in 2017. There were two lots of plastic that it interacted with which are amorphous, and the fused quartz in the Lion reactor is amorphous. And more recently, and hopefully we'll share this data when I've had a better look at it, we've seen fused quartz in the Vega experiments apparently being affected by emissions from the electrodes in there. Okay, so frozen liquid here. So, and if this effect is completely incomprehensible and unexplainable, the explanation, funny, may be sought through the application of the most improbable theories, up to and including the now very fashionable theory of dark matter or energy. I think basically what he's saying there is, as we can't explain this with any kind of normal radiation particle physics type scenarios, then everything is on the table. And what could be more understandable and mundane for this inexplicable process? The quest to answer these questions posed and the experimentally seen tracks on CDs from this, indeed strange, incomprehensible radiation led me, that is our friend that wrote this presentation, to use a new but more mundane model, that of dark hydrogen. And so this is the dark hydrogen, and as far as I understand, and I've looked at it before, it's called T hydrogen. I think it was called a Barut atom or something like that. You can go and look at the previous presentations. But essentially what you've got is you've got I think it's like a Cooper pair of electrons in the core and the protons around on the outside. And the structure spins, or at least maybe the internal part of it spins. And so you kind of like have a boson in the middle. And the actual mass of this structure is the same as normal hydrogen. Of course, it's got 2 protons and 2 electrons. But the arrangement of it is physically different. So you still get the attraction to those 2 electrons in the core. But the way it interacts. Now, this has, I think Zatelepin described it, it has a magnetic component to it. But it's, what does he say? It's something to do with its direction. It's a little bit unique in the way that it works. Anyway, it's best to probably go and look at his work on that. And so essentially there's a suggestion that it's a cluster of these because they are magnetic. And so he says here, to explain the formation of point and helical tracks as the effect of an energy cluster. So he's definitely saying that this is an energy cluster, but in fact, anything with a proton and electron is effectively an energy cluster. On an amorphous medium, glass or plexiglass, a medium of dark hydrogen with its parameters was used by Baranov and Zatelepin. And he presented this in Beijing, China in 2019. Okay, so whilst the West and generally are not taking this seriously, Russia and China and a few people are taking this very, very seriously. And a lot of work is being done in this area to understand this radiation, because they do see it as being at least important to the safety of these kind of these reactors, and even having implications, as I said before, to even welding and working next to cavitating devices and high-speed rotating devices. So here is some drawings, and effectively you've got a cluster. Maybe I can show you here. Is it going to appear? Yeah, there's this cluster here, and the cluster is spinning around, and that interacts in a number of different ways. So a small cluster just goes in and makes a spot mark where it is impacted. If it's a large one, it goes in and it changes its orientation and then travels along the surface. So sometimes it goes in a little way, and sometimes it goes in and then burrows a little bit and then travels along. So that's a suggestion, and it is based on the energy level. So the 0.1 to 0.5 teraelectron volt ones just make a spot, and the 5 to 50 teraelectron volt ones go along the surface. And this is striking. So if you're seeing a lot of spiral tracks, the implication is you've got these huge energy particles coming out of your reactor. Okay. So, and I know Lion will be upset because he's wanted to do this for a while, and there are some other researchers that wanted to do this for a while, but he took the bull by the horns and went to test this strange radiation with a diffusion chamber called a Wilson chamber. Okay, so essentially you can go and look at this on Wikipedia, but you've got a vapor coming up. You normally have some sort of cold thing, or it's like some alcohol or whatever. And you can see in the next slide that it's on a block of probably dry ice in a plastic bag. And this keeps it cold. And he's got these flow lines coming from the top and around to the bottom, and this will be more explainable when you see later in the presentation. But here is the slide, and he was asked, where is the reactor in this image? Well, actually, if you can see my cursor here, he's actually blacked out where the reactor was, and it was over here, and there was a little bit of I got a bit of tension as to why people weren't seeing it here. But anyway, now the next slide is the actual video from the Wilson chamber, and this is I think this is with the reactor running. So you will see some tracks being produced, and what I will do is I will separately publish these videos, and what I will do is I will motion stabilize it. In fact, I've already done it, and I will also clip out some of the strange radiation tracks, because when they break up, it would appear that you can get a better impression of the spiraling nature of them when they break up, or that might just be an artifact of the Wilson chamber. But I'll play this now. This is the non-stabilized version, so you should see this now. So you can see a good number of tracks being recorded here, real time, and I'll continue to play it, but we're about 40% through. In the latter part of this sequence, there's a slowed down section, and you can see a very, very long track, and then in the next slide, we'll replay that. Now, it looks like the tracks are disappearing. They kind of appear and then they kind of disappear down the bottom here. And what's actually happening there is, as this kind of like vapor is falling down, okay, it's colliding with the base. Okay, so that one's just laid itself out on the base. Like I say, you will have the raw video to look at in the downloadable presentation. I will separately see. So you see the slowdown here? Now watch, watch, watch. That huge track, that massive track, it went all the way across the entire chamber. That is an extremely energetic particle. Okay, so I know Lion wanted to do this first, and it's a real shame that he didn't get first to the table of doing this. But anyway, there it is. And in this next one here, you will see that they are replaying that last section. There we go. So that's that very long track that he wanted to draw people's attention to. Okay, now when more than a year or whatever after this reactor was run, they put it into the chamber here, and they ran it, and so you can see there's a track there that appeared. I'll have a drink whilst that's playing. Wow, lovely. Okay, so he's saying here, new 2020 to 2021 studies on the operation of the nickel hydrogen container or reactor at room temperature. A container reactor that has been sitting for 6 months, so it's 6 months after the thermal process, and 1 year and 1.5 years at room temperature has been subjected to research in the Wilson chamber with a magnetic field of 4.5 milliteslas. This is 100 times the Earth's magnetic field. So the reactor container was made over nickel foil. So we know the outside here is made of nickel foil with nickel hydrogen system. So inside this reactor, there's nickel hydrogen, or with either sodium borohydride or lithium aluminium hydride. And it was in a Wilson chamber. The container is 80 by 23 by 12 millimeters, and the width of the reagents, the weight of the reagents loaded into the container is 6.47 grams at a hydrogen content of 0.1 mole. A powerful track that emanated from the container was recorded when shooting for 46 minutes. So you can see this track here coming out, and this is as the vapor is coming down. And again, it's a couple more slides here. The reactor was then monitored by CD for 100 to 170 hours. So there's the cold reactor in what looks like a Petri dish or an ashtray, and then over the top he's got a CD. In fact, it looks like a stack of CDs, but let's say it's a CD for now. And they saw these spot tracks, and if you recall from earlier, the suggestion is that a spot track is from much lower levels of tera-electron volts, even sub-tera-electron volt particles, or clusters rather. But in a small number, there were also screw tracks and other tracks. So there's the straight track here and what they call their screw track. The total number of tracks was 100 pieces, which approximates to around about 1 track per hour. So I think that what they're suggesting here is, if we go back, that this was, even after 1.5 years, they were getting the production of 1 track per hour. Now, 9 months after the Lion reactor, the first Lion reactor was run, Lion had a small piece of the crust from the outside of that reactor, the copper oxide crust, and he heated it up to the operating temperature of his tube furnace in the little robot for 8 hours, and I think that's over 1,000 degrees, and then he put that on some the disposable X-rays, these sort of self-developing X-rays, and it would appear that he observed tracks. And of course, when we did our echo tests in 2017, this was many months after the fuel was produced, but that was producing tracks, and it may actually be the case that that is producing tracks now. And Baranov and Zatelepin showed that after 18 months with their bismuth and alloy sample, that they were able to reactivate it 18 months or 18 months I think it was after, just by putting it into sunlight. So they had already demonstrated by 2018 that this can be reactivated by light coming from the sun, which obviously includes a vast array of different photon frequencies, all the way from infrared through to UV. In the case of the work of Lion, he would appear to have demonstrated that IR, that's heat radiation photons, are able to trigger the effect or stimulate the production of the effect. So whatever was created in the material is either allowed to be kicked out, or it is able to be some structure in there is able to recreate or synthesize the strange radiation and kick it out once it's been set up, initiated. So it says, i.e. the probability of a strange radiation emission from a container under these conditions is on the order of a single emission per hour. The detected tracks, in comparison with those from the thermal process, around about 1000 to 1050 degrees C, were fewer in number and thinner in geometric dimensions during the 2 to 3 hours of operation of the reactor. He's putting in quotes because it's just a cold thing from a previous experiment, indicating a weaker radiation energy. But the reactor, the container, continues to work, albeit with less intensity at room temperature after 6 and 12 months, which is astonishing. This radiation is indeed strange, unclear, it's just a different translation, process. It's an unclear process and a strange, incomprehensible radiation. So the energy of the strange radiation from a container that has been sitting at room temperature for 1 year, and so he's calculated it out here, that it's around about 0.3 tera-electron volts, and he's got this image here of the 10 micrometer pit. The experimental result is this. A nickel hydrogen container at room temperature emits periodically this strange, incomprehensible, all-penetrating radiation after a year with an energy of 0.321 tera-electron volts. How can we explain that the reactor is still working after a year? What is this strange incomprehensible radiation? And how long can the reactor, still work, emitting periodically this strange radiation? And that is the purpose of this paper and what it seeks to answer. So the physical model, the hypothesis of the emergence of strange incomprehensible radiation. So what is already known about the strange incomprehensible radiation? High penetrability. In various crystalline, non-magnetic, weakly ferromagnetic steel, supporting sheet of plant heating element, see photo, and diamagnetic materials, aluminium, in the plant thermal unit. So it can penetrate through all of those. This radiation melts the plexiglass, creating channels, tracks of different geometries, and it has a high energy output. And if it were a light, photon flux, or a single entity, there would be no separation of tracks as observed in the experiment. Consequently, this cluster entity has a mass. It has very small dimensions, and because in polycrystals, where there are many defects with different electrical potentials through which this strange radiation passes, it very much appears that it is neutral charged. Okay, so this is kind of something that if you've been following this channel and our work, you will already know this, but you know, this is what he's saying here. He's suggesting that the dark hydrogen TH2 model satisfies all of these requirements as mentioned above. It's not necessarily what is going on, but it satisfies it. And he does some calculations here, and he does some cluster velocities, and he's saying down the bottom there, therefore we can calculate the number of magnetically coupled T units in clusters of N, this is this T hydrogen, the symbol for T hydrogen, is approximately equal to 1 to 10 to the power 6 units. Fly out of the container in 1 hour at room temperature. So he's saying that a year after this reactor was running, that the amount of hydrogen in one of these things that come out once every hour is 1 times 10 to the 6 hydrogen atoms. That is a lot of atoms in this cluster. The diameter of dark hydrogen, which he calculates here, is 0.1 of an angstrom. It should be noted that the evaluation is done for symmetric cluster form, although a magnetic field with pronounced directionality along the T-axis of the hydrogen cluster should pull the cluster as shown on the slide, which would lead to the cluster's transverse size to a smaller 0.1 of an angstrom. So I don't quite know what's going on there, but you can look at this in your own time. He's saying at the top of the page there, here you can see the diameter of dark hydrogen is 100 femtometers. That's 10 to the minus 13 meters. And so that's the basis of this, but the transverse size is 0.1 of an angstrom. So that, I guess, is the difference there. An estimate is made of the parameters of the strange radiation cluster with energy calculated from the experiment of 0.3 tera-electron volts. The cluster diameter is 0.1 times 10 to the minus 10 meters, and somewhere between there and 0.1 of an angstrom. And then the T hydrogen there is 10 to the 6 units. So this is his little model for the hydrogen cluster and the structure of the TH2 atom. It says, but how and why does such a cluster form which satisfies all of the requirements to explain this strange radiation? The essence of the physical model hypothesis of the emergence of strange, incomprehensible radiation is as follows. It is known that hydrogen in the lattice of nickel is in a proton state. Now, it then goes on, note that the diffusion of the impurity is much slower through point defects of the Frenkel type and mainly through bulk defects. Volumetric defects in crystals are grain boundaries, GBs, double grain boundaries, DGs, and small angle dislocation boundaries, SDBs. Consequently, the concentration of catalyst accumulates is to a greater extent in the bulk defects, GB and DG. Let's assume that energy of these wells is the same, and we will consider the DG energy well. i.e. we have an impurity catalyst trapped by the DG boundaries. And so these are polycrystalline structures, and so you can see on the left here this an array here, and here's some microscopy and some sketches of what you kind of expect. So he's suggesting that your lithium and aluminium here is the sort of catalyst in this area, and you've got your Ni plus, and then you've got your protons, these positive blue dots hanging about in that area. And I guess he's saying 5 to 7 angstroms. Is that what that is? Maybe the distance between them. But the boundaries of the energy well are constantly fluctuating, the phonon component of the crystal. So basically, these crystals are shaking about. Why are they shaking about? They're shaking about because they are heated. The schematic of the process in an energy well or grain boundary with a double grain boundary or grain boundary with a phonon component. So the atoms on the sort of double grain boundary here are shaking about, and they are imparting sort of phonons to the catalyst and the protons in the double grain boundary. Hence the problem reduces to a quantum mechanical one. When the electrons with the hydrogen protons are trapped in the potential well, then we have to consider their behavior in it. But the boundary conditions of the spatial coordinates are not constant and are constantly changing and dependent on temperature and time. So it is clear that solving such a problem for both electrons and protons with a constant energy gain from interaction with catalyst atoms and with the energy barrier, the boundaries of the double grain boundary energy well, which are swayed by the phonon component, that's the thermal vibrations, which if it's in that kind of thermal level that's like terahertz is not possible for today. Good, I hope you're all glad about that. I hope the situation then. But from the experiment, and the energy estimate made above from the particle observations, we know that in about 1 hour, one cluster of this strange radiation is emitted, which consists of 10 to the 6 units of T hydrogen, bound by a magnetic field. The property of dark hydrogen, this H hat 2, is to have a magnetic field. And certainly our experience is these things have a magnetic field. Whether it is this dark hydrogen is a different matter. It's certainly, if it's able to go through stuff, then you could consider it dark. But anyway, is the probability of this process. Then, from all the given data and reasoning, it is possible to present the dynamics of the process taking place in the energy well and make some estimates about the process taking place in this system and consider the process. Now, I didn't get the Russian here, so you'll have to go to the Russian. But essentially, there's this, what I've translated to be a meta atom, and you've got a neutron, which is going to a proton and an antineutrino and an electron here. You've got your nickel atoms here. So this meta atom somehow interacts with your nickel, and you get a neutron coming out, and the neutron splits out and you get neutrinos coming out. What is this sheath around the outside? Is that neutrinos? I don't know, because it looks like the neutrinos going over here. So I don't know. This is the model. It's a theory. On the slide, the proton in neutron decay is highlighted for a reason. So this proton, this is the neutron coming out here. This proton here is highlighted. So he's made like kind of that bigger and made a point of it. it says, is highlighted for a reason. The anomalous behavior of the neutron in interaction with hydrogen metal substances which contained hydrogen drew the attention of the 1930s of the last century to Curie, pointing out the high energy of the process. So there's some high energy going on with this process of this particular proton coming out here that he's referring to. Knowing the structure and number of defects in the material under study and the hydrogen concentration in the defect, it is possible to make an estimate of the reactor's performance over time. So polycrystalline nickel hydrogen after a thermal process 1100 to 1150 degrees C. That's not 11,500 degrees C. That should be a degrees. Number of hydrogen emissions per defect. So he's saying that the number of hydrogen is 5 times 10 to the 13 and that thing there. Using the radioactive decay model, the probability of this process will be determined by the ratio of particles emitted per unit time to the number of particles in the defect. Consequently, the half-life will be 2 times 10 to the 5 hours. In a year, 10 to the 4 hours, that's what a year is in hours, approximately. Then until the half-life, when the hydrogen concentration in double grain defect drops by half, the reactor will run for this calculation 20 years. 20 years. So that's 20 years that this material, once you've set it up, will be kicking out strange radiation. And it will be still kicking it out after 20 years, because this is a half-life, right? It'll be just half of its activity. So one would assume it's not kicking out 1 an hour, it's kicking out 1 every 2 hours. So you are making potentially very special material. So one thinks about, you know, we've seen in cavitation extremely high fluxes of strange radiation, or the effects of similar strange radiation. And when that interacts with metal, we're led to believe that this type of radiation can get stuck in metal, or the structures that made it are stuck in the metal. That means that your metals that have been generating this radiation, they're basically easy to reactivate and get going again. And that's kind of where he goes. Using this hypothesis, a lot falls into place. The transformation of atoms is present, i.e. transmutation. New isotopes of other elements are found. There are also neutrons, but not a cluster of dark hydrogen. Strange radiation. So this might be an issue with translation. It says there are also neutrons, but not a cluster of dark hydrogen, a strange radiation, which with this consideration seems not so incomprehensible anymore. So he's basically saying, yes, if we accept this model, some of the things that we're observing appeared to be possible. And in fact, it was based on that model that Zatelepin produced his strange radiation detector, where when you have nickel hydrogen, nickel prepared, degassed, and at temperature over 200 degrees and below 350 or whatever it is, and then you chuck in fresh hydrogen, you get this big flux of this strange radiation out that appears to spin his magnetic sort of on a fulcrum detector. It spins it round, and that he used the properties that he expects from that to produce that detector. Anyway. So, what could be an indirect confirmation of the proposed model? So, what he did is he used, they call it a blue lamp. I mean, do they mean a black light? Is this a UV? I think it's a UV light, and I think you'll know from looking at the next slide. But essentially, what he's doing is he's got this CD at the top here. He's got this old reactor. I guess it's a year old now, and then in underneath he has a parabolic mirror. And he's put this 40-watt black light light. So here we can see the energy of this reactor must increase, which should the energy of the reactor must increase, which should excite the activity of the emission centers, because lambda is 0.4 of a micrometer, and the energy is 3 electron volts. So of course somehow the photons are coming through the aluminium here, or interacting with it in such a fashion And he's saying that this will then excite the active centers so that they increase their rate of production, and hopefully we will see this on some CDs. Now, here, on the top here, we have 70 here, and 170 hours expositions, i.e. exposing to the reactor without a lamp. So you've got a number around here, and this is 170 hours. So you can see there's an increase here. Now, the people that talk about three-body interactions will just say, well, this is because, you know, you're getting less dust accumulating on here and more dust accumulating on here, and then it scratches and you get more over this. But what doesn't fit that theory is that with the blue lamp, you are getting in 120 hours. So it's between these two. With the blue lamp, you are getting a vastly increased number of detections, even though you are somewhere between the one on the top left and the one on the top right. Okay, so here there's many more detections. So he's suggesting that the light, the high energy light that he's calculating here is 3 electron volts with this 0.4 micrometers, is exciting the active centers, and it's stimulating the production of the radiation. And here they tried, as a control type of experiment, the experiment with a lit 40-watt light bulb. So I guess this is a tungsten light bulb. Now, actually, Parkhomov questioned him and said, look, you know, I did some experiments with 40-watt light bulb, and I was getting some tracks being produced. So the bulb itself may be producing tracks, but that might be the case in both cases of the light bulb. But anyway, the light bulb is producing sort of a normal spectrum of light rather than one that's skewed maybe towards higher frequency UV. And you can see the activity of the radiation centers has not increased. So the tracks from the simple lamp on the left and the tracks from the blue lamp. So he's saying that in that instance, it's comparable with no lamp used at all. So this is just the basic radiation emission that's coming out. And on the right, you can see the comparison with the blue lamp. So for objectivity, it should be noted that it was Zatelepin V and Baranov D who said on their first trip to Podolsk, where I had just started conducting experiments, so this I guess was in 2016. Well, hold on, if he was doing this in 2019 into 20, and the reactor was a year to a year and a half old, then backdate it's 2019, 2018. So certainly it would appear that, you know, after Sochi, there was a lot of excitement to go ahead and start some experiments and try and characterize this radiation. So I would suggest by at least the beginning of 2019, maybe the end of 2018, at least it had started then. You could argue that the nickel hydrogen experiments were conducted before, and he argues that it's in 2016 that he started that. But anyway, the reactor works even after the thermal process, and I don't know how long, and I had to look for this fact. I express my sincere gratitude to them. This is the kind of sincere exchange of information that promotes research, and I could not agree with that statement more. If you're seeing some effect, don't keep it to yourself. Tell people. This is more than about someone's ego. You need to get this information out there. It's when I saw this presentation, it was just so important to just get it out to you, and you'll see a little bit later in the presentation when I get to it why. Okay, so I need to plug in my power here, otherwise my laptop will die. Okay, so, and if the reactor is supposed to work for a long time, many years, and it does, why not do more detailed research on this strange, incomprehensible, and unexplained radiation? I will hold your attention to one thought that came up when systematizing this material. I don't even know whether that's a word. Everything new that we do is a well-forgotten old thing, but on a different level. A spiral of philosophy. And then it says, credit to it was there. So he says that Bychkov and Zaitsev, ether dynamics from the 19th century, Uritskev, transformation of atoms using during tungsten wire explosion, Irian and Wendt in 1922, Zatelepin and Baranov Chizhov energy X-ray peak, 1950s dark hydrogen, and then Chizhov V anomalousness in metal hydrogen systems, and then Curie 1930 superconductivity 1950. So he's basically saying that kind of everything that you're observing with this kind of radiation and what it seems to be able to do, there are echoes in the past, and I could not agree with this statement anymore. And I think it's so important to give proper credit to the people that observe these things. They might not have given it the fancy name that people are agreeing now, but you need to recognize that people actually have observed this. So, about the penetrating power of strange radiation and protection against it. Before I go into this, and this is important, this is very important, this section, has anyone got any questions? Does anyone have any questions? Can you hear me? I don't even know if you can hear me still. Okay, so there's a lot of discussion. That's too much for me to go through right now. If you have a specific question on what I've gone through so far, shout it now, or forever hold your peace. Well, I'll ask questions again at the end. Write down the questions that you have, and then maybe I can do a Q&A right at the end. Okay. What's the black chamber made of? The black chamber. The black chamber. The black light chamber? Okay, so you hear, that's good. I'm not talking to myself. It's useful. Okay. I don't know what you mean by the black chamber. Do you mean... Hold on. Do you mean this chamber? On this left here? Black chamber? Okay. One with vapor trails. Oh, so what is the black chamber? Let's go back to that. Yeah, quick. It's important to know what you're talking about there. So, the black chamber here, it's basically a food jar. I would imagine it's a standard kind of borosilicate jar. Nothing fancy. I think what you've got underneath here is a large block of dry ice, and that's why you're seeing some frosting on here with probably a piece of cardboard underneath to insulate it. And as I've said before, this area up here, this kind of ellipse that you see in here, was where the operating reactor was. And like I say, if you go to the Russian version of the presentation, there's a little bit of a testy moment where someone's asking, "Where's the reactor?" And he says it's under here. He says, well, "What is it? What have you put there?" And I think he wasn't too open about that. I may be wrong in that assumption. So yes, it's a Wilson chamber. Yeah, Wilson chamber. So it's very well known how to do it. I think you put some kind of you have a cold thing down here, and you in this felt. This is normally a black felt. You use literally felt, and you put some alcohol on here, and you kind of get some evaporation and condensation, and you basically keep it cold down here. So how and where do I start my experiment on this subject on a very limited budget? Actually, some of the experiments you can do, maybe I should do a separate video, and that's a good question, on where we are now with the field and what experiments you can do to, get a handle on the basics of this. But there's some wonderful experiments done by Alexander Parkhomov, the woodpecker, and the light bulb experiments, and those are things that you can do whilst you can still get a tungsten light bulb. And the woodpecker is very simple, and also you can do experiments with induction coil from a starter, from the distributor cap in cars. You can get like a second-hand one of those, and you can do these sparks in a non-resistor containing spark plug with spray water. And in one of the videos I shared about 3 years ago, someone noticed one of these large ball lightning type clusters are forming away from that spark plug in the same orientation as the same kind of structure that was shared by the Moscow Nuclear Physics Institute a couple of years later, in fact, by Bogdanovich et al. So you can, if you've got a high-speed camera, and many cameras on phones are high-speed these days, they're not necessarily high resolution, but in terms of what you need. But anyway, you can do those. So I think I'd probably do that. UV tends to pump, and they're arguing that the structure where you've got the right grain boundaries, so this is actually playing into Edmund Storm's kind of nuclear active environment. And in fact, if you actually look at this structure, it's not too far removed from what he's saying. You've got protons with this oscillating electron between, but you can say, they're saying that these packets are magnetic and they align differently. And you'll see that as we move forward. And I'm going to move forward now because I don't want to be caught out of curfew, and there's quite a bit I need to say that's very important in this last section. So let me go to that. Okay, so about the penetrating power of strange radiation and protection against it. So, having found tracks on CDs and glass in experiments, it seemed to me that all strange radiation is 100% captured by amorphous media. Frozen liquid does its job. Where does this radiation go if there is no order or in arrangement of the atoms? Well, the strange radiation must be trapped in this chaos. Makes sense, yes? But when discussing the wire explosion experiment with Aritskev L., where this strange radiation is also present and recorded, I was surprised that his flask is pure quartz, silicon dioxide glass, an amorphous medium, and this radiation passes through. Is this possible? I'll have to check it out. So, it is incomprehensible. It is the incomprehensible behavior of strange radiation, the incomprehensible radiation in amorphous and other media that has led me to the testing and many experiments with different exposure times and a number of other experiments. And what is the penetrating power of this strange radiation, and what could be a protection against it? In what follows, only a squeeze of many such experiments will be reported. So I guess this is a little, it's a very tight selection. So here we go. Experiments were carried out on 3, 5 and 10 CDs to test the penetrating power of the strange radiation. So you can see here, you've got this ancient reactor, which has a half-life of 20 years. You've got the Petri dish coming here again, and then he's got an alignment mark up here, which is quite useful. And then he's got a stack here of CDs. Now, you would suggest that maybe this is absolutely ripe for collecting three-body interactions. And so he's saying, what was surprising was that even the 10th CD there, on the 10th CD, there were tracks of this strange incomprehensible variety. Even this is the number 10. They're still getting tracks. The decline in track concentration up to CD5 is exponential. Okay? So this is, other than the argument that I've been suggesting with using a webcam, which for me is watertight, this is a very good argument for the fact that this radiation tracks detected are not necessarily from three-body interactions, because presumably these 10 CDs in this stack here, let's assume that's 10, they were all placed at the same time. And one would imagine that the first one could collect much more dust, okay? Because it's kind of exposed, at least on the outside. I don't know whether you're going to get much more dust in here, but it's less likely to be a three-body interaction because it doesn't have anything between it and the reactor. So but it is highly exposed, so it's going to get the biggest hits. Okay, but it's these ones. This second one here. So this is, well, he's calling it one. This should be offset one, I guess. This is reactor. This is CD1, and this is CD2 down here. He's saying that this is exponential. Okay. Essentially, the first two have got much higher incidence of the radiation, and this is good from a shielding point of view. But all the way out here at 10, you're still getting a similar number of impacts as you were getting in the 3, 4, 5, and so on. Now, the interesting thing is that this was similar to the Perovskikov experiment, where he was using standard film, and he'd taken some water with some 0.4 Tesla magnet array underneath, and he'd put it out and exposed it to sunlight for a couple of weeks. And then he brought it in and used a kind of laser pointer, pointed it at it, and supposedly this quanta of strange radiation came off and left these marks. But the marks were not necessarily on the first helical part of the coil of the standard 35mm black and white film. Some of them were found all the way into the core. So it's the same kind of observation where it's able to go through and penetrate all the way into other material. Experiments have shown that even a 10-layer sandwich of polycarbonate and aluminium foil, so note there's aluminium on those CDs as well, and there's also a paint layer, to be honest. This is 12mm, does not protect 100% against this very high energy, strange, incomprehensible radiation. And bearing in mind, we're talking about radiation that's emitted 1 year later, and it's not in the 50 or 60 or whatever it is teraelectron volts. This is in the 0.3 or the 0.1 to 0.1 teraelectron volts. So this isn't the intensity of radiation that's coming out when a reactor is live. This is the intensity of the radiation that's coming out when it's a year old and it's sitting there at room temperature, which kind of makes me a little bit concerned that I've got quite a few different Leno experiments that sit around me. Like, you know, this one, maybe I should hang a CD over it, and this one, maybe I should hang some CDs there. Just something to consider. Yeah, okay. So he says, what about the behavior in a magnetic field? Experiments with a magnetic field. This is really fascinating for me. So what you're seeing here is he cut a CD so he could put it at the bottom of the Petri dish, and then he taped on this cold, dead, so-called reactor here on the top here. And then he put another CD on top, and then he had a north-south and a north-south magnetic. So he has what you get between these two magnets is quite a parallel field, a consistent field between here, and then you get the normal sort of donut type field line around here, apple-shaped field, if you can imagine it. But it's fairly parallel between these 2 points. Okay. And so you can see this large block, I guess it's a ferrite type magnet here that he's got. And so you can see here that the one that was under the reactor, you can almost see the reactor shadow. So the reactor is here, yeah, in this center area, and you've got here and here with a couple to the side. Okay, in the one that was above, you've got them kind of around the periphery. So that would mean, you see, it's still not exposed to the air on that point here on many of these tracks. Around the very edge, then you could argue there might be dust interactions. He also noticed these tracks. Now, these are quite interesting, and Matsumoto talked about these ones that looked a bit like single-celled organisms with their bits inside them. So, and he actually said that it literally looked like biology. Okay, so what is remarkable about these experiments is that in small numbers, the tracks are fixed in the form of petals up to 1 millimeter in diameter. So then he tried another experiment, and so this is number 2, discs over the magnet. So rather than having in this straight field area, he put the disc on top and on the far bottom. And this is the pattern that you got observed. So your magnet is effectively between these two lines, and there are a number of tracks on the outside, This is basically on the line. This one is inside the line. On this case, it's inside the line. So here is a protection against this strange, unintelligible radiation, it would seem. Now, do note that in 2017, we showed that by having a magnet, we could direct the emission from the echo fuel through plastic and leaving tracks there, and there basically weren't tracks of that intensity outside of that area. And I really do want to go back and visit that detection material when I can with the right equipment to see like more fidelity about what is around that area. So and in 2012, I think it was, Keith Fredericks also showed that the radiation can be directed by magnetism. And there's one very important point here, is that you know, this will come on to what's being said later in this presentation. I'm getting short on time, so I'm going to need to speed up. In the I think 2019 paper by Bogdanovich, he used a synchrotron to create a high-speed electrons to go through some conversion targets to create gamma radiation, and the gamma radiation passed through two magnets. And he argues that the Birdie type large quanta, that it arranges itself into a sort of, apparently a kind of pseudo monopole, this Birdie arrangement is knocked off by the gamma ray from the faces of the magnet. And he suggests that this is ubiquitous and that it's aggregating on the surface of the magnet. And that was in 2019. Perovchikov in 2012 is using a magnet to focus the radiation, and it aggregates into the water for a very special reason that I will come on in a completely different presentation, in my view. And so it aggregates in the water, but the magnet is allowing the natural flux of this, whatever it is, to be focused into a way that it can be stored in the water. Okay, so we know magnets can focus this and cause aggregation. And in the case of Reactor in 2001, 2002, whenever it was, he had his exploding wire, and 0.7 meters away over here and 0.7 meters away down here, he had some iron 57 foil in both places and a control off to in another place. And on one he put a north pole of a magnet on the backside, and on the other one he put a south pole of a magnet on the backside. And they used nuclear magnetic resonance to look at what had happened to those after the experiment. And what had happened is that one had shifted one way and one had shifted the other way, and the control was in the middle, which implied that some norths go to the south and some souths go to the north and affect the fine magnetic moment of the 57 iron nuclear magnetic resonant nuclei. And so he's assuming and suggesting that this is proof that this produces monopole type structures. Anyway, so moving on. So there is quite a selection now of work spanning most of the last 2 decades that show that this can be controlled and manipulated and even captured by magnets. And this is something that he is effectively saying is also observed by him. Now, he disagrees in this next slide. He says, after conducting such experiments, one could agree with the magnetic monopole models, Dirac or low-shape monopoles, for the formation of strange radiation, although its passage through diamagnetics, 10 layers of aluminium foil, immediately puts these models into question. I disagree. And in the next section of the magnetic signatures of strange radiation, I will discuss why I disagree and why probably the Hutchison samples are the most important evidence to suggest that they do interact with aluminium and so forth. So he's saying aluminium, but he's really talking very thin layer of aluminium. It doesn't say it discounts it completely, but he says it puts it into question. Another thing that was confusing was the behavior of strange radiation in the Wilson chamber, and he's again referring to these tracks in the Wilson chamber. So, you know, what's going on here? because you have this radiation somehow coming out of this nickel foil. And so one would assume it's not alpha. It can't really be, well, you know, beta's going to get stopped by it. Gamma, no, that's not going to do what you see there. So something's interesting is going on. Okay. And this is this high energy track that he observed once every hour or so. So the experiment 3 was CDs covered the reactor and magnets on all sides, and they exposed the reactor, the CDs to the reactor in the magnet field for 120 hours. So what you see is it's a bit like the previous experiment where you got this CD on the top and CD on the bottom, but then he cut some CDs and put them round the sides of the magnets with the reactor in the center here. And so here you see they've got some standard sort of blue painter's masking tape, and here's the cut CDs, and he's put the north-south orientation on this. This is the lovely thing about CDs is they have, oh, hold on, they have these easy to write on top, so you can do all this nice documentation on the actual sample. So it's a wonderful detector if it is reliable. So the result in its manifestation was both expected and highly unexpected. So here we go. You have almost completely protected here on the kind of bit that was on the north side. This is on the south side. Again, much less on the center. These areas, you could argue, well, they're exposed to the air, so could it be three-body interactions? I don't know. But then you have these ones on the side, and they're fairly evenly distributed. But you also have, if you actually look at this quite closely, where you have more interaction here, you also seem to have more interaction here. And where you have more interaction down here, you seem to have more interaction here. And given the geometry of this, it really doesn't seem to me to be three-body interactions, these detections here. And this method of actually looking under the microscope and then getting a marker pen and marking where the tracks are, I think it's quite a nice approach. So he does this drawing here, and he's got these spinning sort of north-south like trains of material flying in and then attaching the south end here, attaching to the North Pole here, and the North Pole here attaching to the South Pole here. So, you know, it's kind of, and each one of these is these magnetic units of this T hydrogen in one possible outcome here. And he says a diagram of the process can be presented as follows. The reactor here in the center, you have the big north on the top here, so south underneath, and you have the big south down here with the north on the top. And so he's suggesting that all the south oriented ones go down here and all the north oriented ones go up here. And this is a kind of something that would fit potentially what was observed by the work of Laureate and also the work of Baranov, so forth. And certainly I can't argue because I just had a magnet. The magnet when I ran the experiments for strange radiation on the echo fuel, I don't know the orientation. Something my faux pas when I did that. I should have done the orientation, but I'm quite encouraged to think that I could take that sample, leave it in sunlight for a period of time, and run some experiments, because it would seem that cavitation produces very, very intense sources. Almost like I'm scared of the echo sample. I really am. I'm not really scared of these samples that I've got around me, but I'm scared of the echo sample. So he did this wonderful experiment here where he did the reactor, the cold reactor, put it between those two magnets. You see those two ferrite magnets, and then round the outside he used magnetic vinyl film. And this is the sort of thing that you have on fridge magnets, that it's made out of fridge magnets. And this is, for me, the big contribution that has been done by this work. And so he's got the CD at an angle, and you can see the arrangement. Arrangement here. So he's marked on the experiment on the back of here in the date, and so it's very convenient, the CDs. So you can see this magnetic vinyl film and the ferrite magnets here, and this is the result. Magnetic vinyl film protection worked, but there was a gap between the main magnets and the film in the experiment. And so what he's suggesting is that the gap here between this ferrite magnet and this, the radiation came in, went along the edge, and then got caught on the edge. Now, one could argue, if you were in the three-body interaction argument, that what happened here was it was just contacting the surface here, and you got some scratchy marks. So, you know, this for me isn't quite so convincing, but we can reasonably argue that there's not a lot of tracks down here. He doesn't say how long this was exposed for, which I think maybe is something that needs to be clarified here. As they used to say on the Rusi, that's all for now. Learning goes on, must be continued. So he has some conclusions here. By thermal nickel-hydrogen process, research has shown that this process senses excitation from electromagnetic oscillations, i.e. if you use AC, you're getting a factor of 20 more, 20 times the amount of temperature deviation around the nominal when you are using AC. And it says, which necessitates the search for resonance and its control, because not all oscillations will produce the same level of deviation. Some might produce a hell of a lot more, and that's something to bear in mind. In this case, it is possible to expect major breakthroughs in obtaining coefficient of performance. That's the output over the input. Continue research on protection against this strange, incomprehensible radiation. To do this, the search must be directed towards optimizing the geometry of the magnetic fields and their force action, i.e. finding ways of reliable and cheap protection against such energy. Okay. 3. To carry out a more nuanced study of the operation of the reactor, this cold thing, and therefore it's great because once you've made a reactor, you can do experiments with it for 20 years and it's only going to be half as active, is what he's suggesting. And therefore, to understand more deeply the processes involved, a very tempting perspective on the operation of the generator reactor. What do we have for researching this process? Well, amorphous foils, waxes, glass, CDs give you tracks. The Wilson diffusion chambers, you get tracks appearing in that. And taking a general X-ray background, that's it. Well, I disagree, and I'm going to argue that there are other techniques. I've already mentioned the one that I developed using Cosmic Ray Finder and a webcam. I would like a much, much thicker CD. And for those out there that are listening that are capable of producing this, the person that developed the muon detectors, actually in Santa Cruz, they have very thick CCDs, and that allows the path of the energy of the incoming radiation to interact to a deeper depth. Now that is more relevant for muons. It may not be so relevant for this type of radiation that tends to hit a surface and then either bounce off or go in and then travel along the material. And since the reactor works and continues to work at room temperature, why not try a Mossbauer study into the dynamics of the reactor? What is actually going on in there? Yes, this is unique and expensive research, but the resolution in these studies is as high as 10 to the power minus 25 joules, right? It is possible to get very interesting results. So we may see them doing Mossbauer studies on this reactor. They've got it. Why not? Why not? So I would like to express my gratitude to the managers of the Moscow FIZPRIBOR plant, Ian Chizhov and S.I. Safanov, for their support in the research presented. Thank you for your attention. And I hit the mark just after 2100. Now, just to think about the implications for the safety here, I went and looked ahead at what the price is of this film, this polyvinyl magnetic film, and you can get a 24 by 10 foot roll of this material for $48. And I think that's even with free delivery. With this amount of material, at least this aspect of the radiation you can collect. Now, our work, the work of Perovskikov in 2011, the work of Roitskev in 2001, and the work of Bogdanovich in 2019 would suggest that the radiation, if it is this quanta that can be moved around, so Bogdanovich is saying if you get high energy radiation, in his case gamma rays, hitting a magnet, you are knocking these things off which are actually stuck to the surface of the magnet. Okay. In the case of Perovskikov in 2011, he's suggesting that when you put a laser, just a milliwatt lasers into water, where you've aggregated these clusters and they've been captured into the water by using a magnet to capture them into aspects of the water, you are able to release this later. So it's captured in the water, and Bogdanovich is saying it's captured on the surface of a magnet. And in the case of the work of Reactor, he's saying that a magnet directs it to be captured onto the nucleus of the iron 57. So what I would suggest is, if you are using this as a method for shielding, I would use another aspect of these type of materials, is to wash them after you've done an experiment in iron-rich water to prevent buildup of this material on the surface. Okay? Because if it builds up and builds up and builds up, you get from being the little spots to the long chains to being the magnetic monopoles. And so on the flip side, that you can think about ways to employ that technologically also. Now, I want to refer to something that I published in 2018, and this is the last slide of a new form of penetrating radiation by Shishkin, and it's talking about shielding at that time. Yuri Bazhatov had died that year, or within that year, and his wife had said to us that after 30 years of experiments in this field, and working with these types of radiations, he established that you need these to protect workers: fluoroplastic plate or boron. Now, I will do another separate presentation on shielding overall, where I'm standing with my understanding of it now, because it's too important to too many people that they're not exposing themselves to this. It says the thickness of the sheet of glass or something, it must be 2 centimeters thick. Now, this was his experience. There's no talking about magnetism in here, so this is a different situation we're in. Ken Shoulders and Alexander Shishkin's work both suggest that many thin layers of conductor and insulator, say metallized mylar sheet. This is why I created the aluminium and cellophane. So cellophane is made from cellulose, and it's biodegradable, actually, just interestingly. And I made multiple sheets on a piece of polystyrene. The recent Russian research, and I'll go into this in more depth, has shown that if you have aluminium, it seems to be quite effective. If you use heavier elements, all you do is you end up by causing more DNA damage, because the strange radiation captures ions of the heavy metal that's going through. Let's say you're trying to use lead, and then it has more of a punch when it interacts with your biology. So they found that aluminium is pretty good, and in fact they used beryllium, but beryllium's toxic in its dust form anyway. So I would suggest boron, and I will talk about how we can possibly make very, very cheap radiation that learns all of this. Because of the Bremsstrahlung radiation, which we believe we observed in 2016 in GS 5.2, you might want some lead shielding after you've got all these other types of shielding behind it. But this bit of inspiration, which as an experimental foundation by this author of using these magnetic vinyl sheets, I think is a good one, and I would consider putting those behind. Now, in terms of fluoroplastic, it is interesting that one type of vinyl, and this is not in the original presentation, but I just wanted to put this in here at the end because I think it's very important for it to be grouped here for people to catch it. You can get polyvinyl chloride, but you can also get polyvinyl fluoride. Now, my ideal material would be polyvinyl fluoride sheeting, which is a magnetic vinyl. That would be fantastic. And we've already appeared to have shown that fluorine interacts with strange radiation, and I will talk about that in some experiments that came out of, in fact, with ECHO, actually, interestingly enough, and we'll talk about that another time. But anyway, I found a commercial product which looks like it's going to be fantastic. And it's readily available. I don't know the cost yet, but people can look into that. It's more expensive than this very, very cheap magnetic material here. But I think you can combine the two to get a reasonably effective shield. Now, I'm saying this on the basis of my best understanding at this time. It's not advice for people to go out and do really dangerous experiments and rely on this for shielding. But I'm saying, with what we know, our own MFMP research, my own personal research, the research of the international community that is interested in not having people die from exposure to this radiation, which you, as I said before, will likely be getting from welding and from anything that cavitates and from anything like, fast spinning bodies. There's this, and this is a backing material for solar panels, and it's fantastic in many ways. Firstly, it has this material that's produced by DuPont, this PVS, so this polyvinyl fluorine. Okay, so it has that. It has an aluminium sheet, which the Russians, testing with mice from a cavitator, I think it's a cavitator, have shown that aluminium does have some shielding benefit. Then it has often an adhesive layer as well. But what's also great about this is it has a high dielectric strength. So I would suggest some iron-rich water. Possibly I would use borax in the iron-rich water. And I will draw diagrams of this, but I would suggest getting an old double glazing unit, mixing borax in the water and filling the double glazing unit. There's something I would put in front of that, but that's a different, that I will do in the group presentation. Behind that, I would like to have some of this Dunsolar 1700 TAPE. And then behind that, I would have the magnetic material. And behind that, for belt and braces, then I would have the lead. I definitely wouldn't want the lead at the beginning of all this. I potentially want the lead at the back to stop the bremsstrahlung radiation of any remaining material coming through. But I would hope that the PVF and so on. And now the PVF is not like 2 centimeters or whatever it was that was said. Where is it? It's here. Here, this 2 centimeters thick. It's not that thick, but it's 2 centimeters. Yeah, 2 centimeters thick. But I believe this combination, with my best understanding at this moment, would offer the best protection from this radiation. And I believe that whilst I do know that probably the reactor contributed to the death of its maker, the supernova reactor, that I'm nearly ready to have the protection that I'm comfortable with running the reactor. So any questions before I go, because it is basically the end of this session here, and I need to get back because the Czech Republic has the worst number of deaths in the world per million people, and as of probably tomorrow, of any country that's got over 35,000 people in it, which there's only 2 that are worse. And so, well, what I would suggest, Gardi, and any other questions, I would suggest going to remoteview.icu, where I will be uploading the presentation, slide material, and the stabilized Wilson chamber videos, and some GIF animations of those key tracks and so forth. I would suggest you answer the questions there, because I will be more likely to interact with them there. I think from my point of view, this spiraling is going to be very important, and I encourage you, if I can get it together, I'm going to hopefully work very hard tomorrow. There's some findings that we're finding with Vega, which I think are absolutely astonishing, completely astonishing. And you are going to love seeing what you're going to see tomorrow. But it all plays into potentially why we're seeing certain tracks in the way we are through the history of this research and so on. And so I want to thank the author of this presentation here, because it's a great piece of research in my opinion. It's built on the research that you in the community helped the MFMP conduct, and I'm very happy that I've had the opportunity of working with Alexander Parkhomov and having a better understanding of this, and I'm looking forward to meeting Matsumoto, discuss his feelings about these things moving forward. Corky, it'd probably be about the same time, but I will publish probably around about 1 or 2 o'clock in the afternoon, the time that the live stream will go out. I'm kind of happier with the setup today. If people would prefer another language for the real-time non-English transcription, then let me know. But I know that in terms of the people that I know want to be able to understand this immediately, there are some people working on reactors in Italy, and so I chose Italian tonight, and that's why that's there. So I'm going to just see if there's any questions, and then I'm going to call it an evening in the next few minutes. So Axel, I do tend to agree that the radiation is produced when the EVO explodes. I do tend to agree with that. Certainly, we have seen something that would suggest that with the ECHO material, and that's been observed, it would seem, with the work of Matsumoto, and it's implied by the work of Adamenko. Specifically, when you get to a certain cluster size, it has a self-compression mode, and it goes in and it forms a boson over and just goes boom. And there are certain parts of that self-compression structure that aren't sufficiently completely turned into light and electrons, and those are subquanta of strange that form the strange radiation, but subquanta EVOs. Boric acid solution, yes, boric acid, yeah, but I mean, borax you can just buy in many countries, and in fact, in many countries that don't sell borax, you can buy it on eBay because people use it for making slime. So there are vendors everywhere because kids like to make slime. So. The good thing about this polyvinyl fluoride backing material that I'm suggesting here is that it's designed to run at 90 plus degrees centigrade. So you could, if you had water accumulating energy and boiling off around that water chamber, you could have this and it would be able to work for a very long time. The reason it operates at that temperature is because it's on the back side of solar panels, and it needs to be UV stable, which is important, bearing in mind what we said here, and it needs to be thermally stable for 20 plus years, in a solar panel. So I think this in combination, and I like to say, I'd like to know how expensive this is, but in combination with the magnetic vinyl is potentially a very good combination shield, and you could literally wrap your reactor in it, and possibly quite affordably. Gardy, no, please post me some links on the tri-layer twistonics. I know there's some theoretical stuff and computer simulations on various vorticey type concepts, but for me, I like to see things and work with what I can see. Thanks, Julie. Okay, Peter, just fire the questions into remoteview.icu. The reason I'm asking people to put the questions in there is that I can answer them there, and then with the article and the supporting material, everything's collected together for people, so they don't have to ask the same questions. It helps me. It helps the people looking. The Evo is unstable at large sizes. Yes, Axel. No, once the active material is set up in the reactor, it doesn't need to be hot. And from my point of view, the work of Adamenko, where he produced these structures that were effectively sort of producing Hawking radiation when he was firing ions into them, it was quite fascinating to me, that shared in 2006. So basically, he was firing primary ions in a secondary ion mass spectrometer, and there was no secondary ions. There wasn't even primary ions, and they switched off the device and the photomultiplier, and they saw this glow and exponentially decaying. And so, this is a cold accretion disk from one of their experiments. So something in there was working at room temperature and eating matter, and partially at least converting it into photons. Yes, Blues Doctor, but I think from my point of view, there's two aspects. He says there's not many ways to detect this. I disagree, and I'm going to talk about some others. I talked about the potential for using 205 thallium and 205 lead, and I'm going to add the support material to that presentation on remoteview.icu. But there is this question that I've been discussing with you. My issue is the difficulty of detecting something, an isotope that is just an electron mass difference, and it's the same with nickel 64 and zinc 64. It's very difficult without extremely high resolution ICP-MS to be able to be sure about that, and so maybe a combination of techniques or extremely high ICP-MS might be appropriate, or chemical techniques. That's a big question, Gardy. It's not one to answer at this time. Okay, will you put the link to the write-up below? I will put the link in the description to the video, yes. But if you go to remoteview.icu, it's the current open article on there, and in that article I will be putting the links to the English and the Russian versions of the presentation. My English one has these extra slides at the end with the links, and so I'll have to say thank you very, very much for your time. I also want to thank Bido. He's enabled me to purchase a couple of items that has enabled me to make a much more effective presentation now to you. So this reduces my stress when I'm doing the presentation, and hopefully the quality is higher. There's one issue: for some reason it's giving this nice warm tone to the PDFs when actually they're quite white when you look at them. So I need to resolve that. But I'm thankful to Bido now, and I want to thank all those people that donated to the project over the years, because you're now really getting to see the benefit of the faith you had in us and the work that we've done over the years. And I'm really excited as soon as the lockdown is reasonable and I can travel and so forth. We have some fantastic experiments set up. Fantastic verification of experiments by people like Hudson and by Yul Brown and these kind of things, and also more work with hopefully with Matsumoto, and more work with Amasa. And so there's some really great things coming down the pipeline, and I'm also quite excited to think about what I've got around me, and reconnect with the fact that I have these samples, particularly the echo sample, which I could probably break up into multiple samples and send to people for them to study this radiation by re-exciting the material into an active state. And so that's something I really need to think about. Because but it in past I've, like for instance ICCF 21, I handed out samples to 7 groups, very competent groups. I've not had one piece of data back from 7 groups, so I'm a little reticent to hand over material now to people that promise a lot of things and deliver nothing. Because this material, it took a lot of community money to acquire. You get data from the likes of Alan, myself, and by the way, I've got something really exciting to announce for the community that has been produced, and so just look out for something in the coming week. But I think it's going to be a benefit to the whole community, as I hope this discussion on ways to shield for this radiation is helpful also. So with that, I'll say thank you very much for your time, and I will see you soon, hopefully tomorrow evening.